All right, in this video, we're going to look at some examples of finding inverse functions for various functions. So we're going to start with f of x equals 5 times x. So here, in the last video, we looked at not only switching individual points, but also the steps in finding the inverse function itself. So we could create a general rule that will apply to all points on the graph and not just maybe one or two. So our first step with finding the inverse for f of x equals 5x is we're going to rewrite this as y equals 5x. And that's just to make the notation easier to work with. Our second step is we're going to switch the x and the y. So we have x equals 5 times y. And I'm going to make my y's in red so I remember that's what I'm trying to get by itself. That's what I'm trying to solve for on the right-hand side. Our third step is to solve our equation now for y, or in this case, red y. We're going to solve this equation for y, and then we'll rewrite our answer using inverse function notation. So to solve for y, we're just going to use the inverse operation of multiplication, because we have 5 times y, and the inverse of multiplying by 5 is dividing by 5. So divide both sides by 5, and we get y equals x over 5. And so using inverse notation, f inverse of x equals x over 5. And so what this will do is it will guarantee that any input we give our original function, if we take the output we get and put it into this inverse function, we'll get our original input back. So for instance, let's say in our original function we plug in x equals 2. 5 times 2 is 10. If we put 10 into our inverse function, 10 divided by 5 will give us our original value of 2 back. So this inverse function will guarantee any output we get from this function, we can put into this inverse function and get our original input back. Part B, f of x equals 3x plus 2. So we'll make it y equals 3x plus 2. Switch the x and the y. And we want to solve for this y. So first thing we're going to do is get rid of any addition or subtraction. So we'll get rid of this plus 2 by subtracting it from both sides. So we get x minus 2 equals 3 times y. And then to get y by itself, if we're multiplying it by 3, do the inverse operation of multiplying by 3, which is dividing by 3. So we get y equals x minus 2 all over 3. You could also make this x over 3 minus 2/3 or 1/3 x minus 2/3. That's fine as well. So our inverse function for 3x plus 2, f inverse of x, is going to be x minus 2 all over 3. Part C, x plus 5 all over 7. So it's a little bit like the last problem's answer. So let's make this y equals x plus 5 all over 7. And then we'll switch our x and our y. Red y, red y. And now we want to get this red y by itself. So let's get rid of this fraction by multiplying both sides by 7. So we get 7 times x equals red y plus 5. And to get red y by itself, we want to subtract 5 from both sides, and we get 7x minus 5. So our inverse function is 7x minus 5. Part D, g of x equals x cubed plus 1. So we'll make it y equals x cubed plus 1. And switch the x and the y, so we get x equals y cubed plus 1. So get rid of this addition of 1 here by subtracting it from both sides. You get x minus 1 equals y cubed. And then to get y by itself, if it's being cubed, our inverse operation for cubing is cube rooting. So if we take the cube root of both sides, we get the cube root of x minus 1 equals y. So our inverse function, g inverse of x, equals the cube root of x minus 1. If you put f inverse of x, I mean, that's just it's an easy mistake to make. It's not the end of the world. But just technically, since this original function, x cubed plus 1, was g of x, the inverse should be g inverse, not f inverse. But again, it's not the end of the world. All right, part E, h of x equals 4x to the 5th minus 1. So we'll make it y equals 4x to the 5th minus 1. And switch our x and our y. We get x equals 4y to the 5th minus 1. Now to get this red y by itself, first we're going to get this minus 1 over to the other side by adding it. So we get x plus 1 equals 4y to the 5th. Multiplication next, we're doing reverse order of operations. So first addition and subtraction, going backwards, and then multiplication and division before we deal with the exponent. So to get the red y to the 5th by itself, we got to divide both sides by 4, and we get x plus 1 all over 4. And then to get the y by itself, if it's being raised to the 5th power, take the fifth root of both sides. So we get y equals the fifth root of x plus 1 all over 4, which h inverse of x is the fifth root of x plus 1 all over 4. All right, part f of x equals the square root of x plus 3. So we'll make it y equals the square root of x plus 3. Switch our x and y, and we get x equals the square root of y plus 3. And the y plus 3 is trapped inside of a square root, so we want to do the inverse operation of square rooting for both sides, which is squaring. So when we square both sides, we'll get x squared equals, when we square a square root, that's going to free up what's inside. So we have x squared equals y plus 3. Then to get y by itself, just subtract 3 from both sides, and we get y equals x squared minus 3. So using our inverse notation, we have f inverse of x equals x squared minus 3. Part g, we have g of x equals 5 over x. So y equals 5 over x. Switch our x and our y, we get x equals 5 over y. We could think of this as x over 1 and then cross multiply. When we do that, we get x times y, which is xy, equals 1 times 5 is 5. Or just multiply both sides by y to clear out your denominator and get rid of your fraction. You'll still get x times y equals 5. Again, we're solving for this red y. So if the red y is being multiplied by x, we want to divide both sides by x, and we get the red y equals 5 over x, which our inverse function for g is 5 over x. And yes, it is possible, as we've seen here, that a function can also be its own inverse. So for instance, let's say we plug x equals 5 into our original function. The only value we're not allowed to plug into this function is 0. So if we plug in x equals 5, 5 divided by 5 is 1. If we take that output of 1 and plug it into the inverse, 5 divided by 1 gives us our original value of 5 back. So it is possible for a function to be its own inverse. Now, visually what happens when you find the inverse, in that second step when you switch your x and your y, from a graphing perspective, what's going on is your original function, by switching your x and your y in that second step, gets reflected across the diagonal line y equals x. So here in red, I have the graph of 3x cubed minus 1. The graph of f of x is 3x cubed minus 1 is in red. In blue is the inverse of that function, which is the cube root of x plus 1 over 3. That's in blue. And here we have the diagonal line and dashed diagonal line y equals x. Notice that these two graphs, the red graph and the blue graph, are mirror images of each other over this dashed diagonal line. So essentially what happens is when we switch our x and our y, every single point gets switched when we graph the function, which reflects it over this line. So I'm just going to pick on, let's just say this point, I don't know what the exact coordinates are off the top of my head. Let's say this is at 1 and 5. Then switching 1 and 5 for the inverse gives us 5 and 1. So these would be the same distance away from this dashed line from the red graph and the blue graph for all those points. So by switching your x and your y, you reflect this original graph in red over this diagonal line to get the graph in blue. And that's gonna we're gonna need to keep that in mind in the next video. So that about does it for this video. Thank you for watching, and I'll see you next time.